What's up, my pre-calc people? I'm Michael Princhak, and in this video, we're going to do a quick recap of Unit 2 for AP Precalculus. Now, Unit 2 covers exponential and logarithmic functions, which covers, well, quite a lot of information. But we're not going to focus in on all the teeny tiny details in this video. We're just going to hit the big concepts, the big ideas that are going to enable you to review and prepare and pass the AP Precalculus exam in May. So let's dive into those big ideas and big concepts right now. So the first thing that comes out of Unit 2 is sequences. We have two different types of sequences, arithmetic and geometric, and here is the formula for an arithmetic sequence. Now, an arithmetic sequence is a sequence that increases or decreases by the same value over and over and over again. Like it goes up 3, up 3, up 3, up 3, or down 5.2, down 5.2, down 5.2. Now, the value that we go up or down is called the common difference, because if you subtract any two consecutive terms, you'll find that common difference. And here's the generic formula. For some kids, this generic formula is a little bit weird to figure out, but let me explain to you. So n is any term you want to find. So if you want to find the 5th term, you plug in 5. If you want to find the 17th term, you plug in 17. Now, the cool thing about sequences is that the inputs can only be positive whole integers, right? So 1, 2, 3, 4, 5, the counting numbers we call them. Now, what is k and what is a sub k? Well, k is any term you want it to be, and a sub k is the value of that term. So if I know the 3rd term, then 3 goes there for k, and the value of the 3rd term goes right there. So in a problem, the common difference d should be known or given. Again, n is any term that you want to find. So let's say that we're talking about this sequence right here. Okay, so the first thing we want to figure out is what is that common difference? What are we changing by? Well, it looks like we're going up 5, and then we're going up 5 again, and then we're going up 5 again, we're going up 5 again, we're going up 5 again. So we're going up at a constant rate of 5, which makes arithmetic sequences the same thing as linear functions. But again, with a function, you can plug in any value you want. You can even plug in decimals or fractions. But with sequences, you can only plug in positive whole numbers. Now, the next thing we want to do is build this function. So any term we want can be found by figuring out any term, right? We just need one term. So literally we have, right here we have 6 options. So what term do we want to use? So let's just say we want to use the 4th term. The 4th term is 7. So that term value, 7 is going to go there. We're going to hit plus 5 for that increasing of 5 every single time. And then we have n minus 4. This will generate the formula for the sequence. Once again, keep in mind where all these numbers are coming from. 4 is the term number. 7 is the term value. I could have chosen any of the other terms and I would get the exact same ending equation. Now all I got to do is clean this up real quick. So again, that's going to be 7 plus 5n minus 20. And of course, I can combine the 7, the negative 20, and I can get 5n minus 13. Now, the cool thing I like to do is check it, see if it works. Let's plug in 2 to find the 2nd term. 5 times 2 is 10. 10 minus 13 is negative 3. Voila, it worked. But again, I can't emphasize enough that you could actually try any term you want. Basically, what we're doing is we're using point slope form. If it was a linear function, 5 is the slope, that's what we're changing by, and we're choosing any one of these points, which we're calling terms. So let's actually choose the 6th term now. So the 6th term is 17. So any term I want would be starting with 17, that's the 6th term, plus 5, that common difference, and then n minus 6. The 6th term is 17. Clean this up, 17 plus 5n minus 30, and we get a sub n equals 5n. Combine the 17, the negative 30, and of course we get negative 13. The exact same formula that we got earlier. Pretty simple. So key things to keep in mind, arithmetic sequences are equivalent to linear functions with the only exception of the domain, what you're allowed to plug in. Functions, you can plug in anything you want with linear functions, but with arithmetic sequences, you can only plug in these positive whole numbers. But building that sequence, building that formula for any term is really simple. All right, a geometric sequence would be equivalent to an exponential function. So here we go, very similar setup here. So R is what we call our common ratio. It's what we're multiplying by, because a geometric sequence, we multiply by the same value over and over and over and over and over again. And that's R, what we're multiplying by. n is the term that we want to find. So if we want to find the third term, we plug in 3 for n. And then k in g sub k, well, that is, again, any term you want. Okay, if you're talking about the third term, k is 3, and then g sub k is the value of that third term. So let's look at a quick example of this as well. So here we see we're multiplying by 3, multiplying by 3. Now to find that common ratio, which we call r, all you gotta do is divide any two consecutive terms. 12 divided by 4 is 3, 36 divided by 12 is 3, 108 divided by 36 is 3, 324 divided by 108 is 3. We're clearly multiplying by 3 over and over again, which means our common ratio is 3. Now it's time to build the sequence. All right, let's use the third term. The third term is 36. The third term is 36. Okay, so here we go. To build a formula to find any term we want, we're going to start off with 36. That's the term that we picked. Then we have our common ratio r raised to the n minus 3. Voila, it's that simple. There is now our formula that can find any term we want. So again, let's check and see if it works. Let's actually plug in 2. So we get 36 times 3 to the 2 minus 3 is negative 1. That's going to be 36 divided by 3 because 3 to the negative 1 moves that to the decimal, or the denominator is 3 to the positive 1. And 36 divided by 3 is 12. So there you go. The second term is found by plugging in 2. And when I did that, I got 12. Now, a lot of people like to write geometric sequences in this particular form, where we have a value a times a base b raised to the n. Now this is more of that exponential form. So you say, well, okay, how can I take this sequence that I got right here, and how can I turn it into that geometric form? Well, to do that, all we need to do is use our rules of exponents. So I'm going to have 36. Then I'm going to separate that 3 to the n and that 3 to the negative 3. Remember, when you have the same base, the rule says that you can add your exponents. So all I'm going to do is take that n minus 3 and split it apart with multiplication. So we have 3 to the n times 3 to the negative 3, and that would be equivalent of 3 raised to the n minus 3. Then I'm going to take that 3 to the negative 3, and I'm going to move it to the denominator where it can become positive. And then I have my common ratio 3 raised to the n. Now, 3 to the third is 27. So basically I have 36 over 27 times 3 to the n. And then, of course, you could reduce that 36 over 27. Both of those numbers are divisible by 3. So that's going to be 4 thirds, 3 to the n, or both are divisible by 9. 36 divided by 9 is 4, 27 divided by 9 is 3. So again, now we have the formula that is more in that generic a times b to the n. And again, all I had to do was use my rules of exponents. So got a little bit ahead of myself there, but again, geometric sequences, exponential functions. The only difference is the domain for sequences are only positive whole numbers, 1, 2, 3, 4, 5, 6, and so forth. And it's really easy to utilize that formula, and you could use any term you want. All you got to do is find that common ratio first. All right, now let's turn our attention to exponential functions, since we kind of were just leaning towards that. Exponential functions look like this: a times b to the x. Now, it's important that we recognize them, because what happens here is with an exponential function, output values of general form exponential functions change proportionally as input values increase in equal length intervals. So what we're going to see is we're going to see our input values go up in equal lengths. Like maybe they go up 2, 3, 4, 5, 6, 7, and our output values go up proportionally, which means they multiply by a common ratio over and over and over again. So that's one way that we can recognize exponential functions that's taught in AP Calculus. Now, another thing we could think of it is this, right? It's the same kind of idea. Output values are going to change multiplicatively, right? So output values are multiplying by some value, whereas the input values change additively. That's another sign, especially if you have an input-output table. It's an easy sign that you're recognizing, or that you're going to see an exponential function. Now let's talk about the graphs of exponential functions. So the graphs of exponential functions all kind of hinder on A. A could be positive or A could be negative. So we're going to kind of talk about that in a second. But they also hinder on B, right? B is always going to be positive, and B could be greater than 1. And if B is greater than 1, we have what we call a growth function. That means the function is getting bigger. So if b is greater than 1, your function is going to get bigger. So here is a graph of this function where a is greater than 0, okay? Now, functions are pretty cool. They just get big, and they get big fast. Now, I want you to notice that there are no zeros. That graph will never cross the x-axis. for this generic exponential function. And it's, there's going to be a horizontal asymptote to that left-hand side. So if we think about end behavior, the limit as x approaches infinity, that's the right-hand side, is going towards infinity. And the limit as x approaches negative infinity is going to be 0. It's going to get closer and closer to 0, but it's never going to get there. Now, other characteristics that we see here is that it's concave up, meaning that the rate of change is increasing. So if I think about the rate of change as I progress through this function, the rate of change gets bigger and bigger and bigger because it's growing multiplicatively, right? It's getting bigger at a proportional rate. So there's my rate of change, there's my rate of change, there's my rate of change. Notice that the rates of change are getting steeper and steeper and steeper, and that's again why it's concave up throughout the entire graph. There's no mins, there's no maxes, a pretty easy function there. Now, if that a value happens to be less than 0, that's going to cause a reflection across the x-axis. Now, this still is technically considered a growth function if your b value is greater than 1. But I look at it like this. We're growing, but we're growing in a negative direction. We're getting more and more and more and more and more negative. So that's still growing because we're getting bigger in a negative direction, technically, but that has that reflection where it's now going like this. So now we see that this is concave down. So we have a rate of change that's decreasing. The rate of change is getting more and more and more negative. And when your rate of change is getting more and more negative, you're going to be concave down. So hopefully that graph makes sense as well. Now, what about if your b value is between 0 and 1? Well, this is going to create what we call a decay function. Actually, oh my God, I can't believe I did that. That should not say growth there. Scribble that out. That should say decay function. These functions are decaying, which means that our output values are getting smaller and smaller and smaller and smaller and smaller. But there is that horizontal asymptote at 0. So the limit as x goes towards infinity is going to be 0. And the limit as x goes towards negative infinity is going to be positive infinity. It's actually going up on that left-hand side. So again, we see that this function is decaying. Pretty simple, not overly difficult. Again, concave up. Why is it concave up? Well, our rates of change are always negative because the entire function is decreasing, but the rates of change are getting less and less negative. So the rates of change are increasing in the sense they're getting less and less negative. Even though they're staying negative the whole time, the function is always going down, getting closer and closer to 0. But it started off going down very quickly, and then at the end, it's going down slower and slower. So again, the rate of change is increasing because they're becoming less negative. It's like a negative 100 to like a negative 2 to a negative 1. So again, the rates of change are on a number line getting bigger, which means it's still concave up. Now, if that a value is negative, then we're going to have a reflection across the x-axis. Once again, this is not a growth. This is a decay. That's a typo. I'm so sorry. So again, this is a decay function. I said, well, wait a minute, isn't this function growing? Yes, it's growing, but it's growing at a slower and slower rate, right? So it's getting bigger. I mean, this function is definitely increasing throughout this function, but notice it's concave down, so our rate of growth is getting slower and slower and slower. So our rate of growth was really, really steep in the beginning, and then it gets less and less and less. So when the rate of change is going down, you're concave down. So those are different types of graphs, and you can kind of get a feel. If you just know those ideas about the b value, greater than 1, it's going to be a growth. Between 0 and 1, it's going to be decay. But then don't forget about if that a value is negative, it causes that reflection. So really think about that if you're asked about concavity and different things like that. All right, let's do a quick review of some of those exponent rules. This is really more of an Algebra 2 thing, but worth us to quickly go over. I kind of already mentioned these rules earlier. When you have the same base and you're multiplying, you add your exponents. Same base and dividing, you subtract your exponents. A negative exponent does not make you negative. It just moves you to the denominator where you can have a positive n instead of a negative n. And then when you have a power raised to a power, same base, power raised to a power, that's when you multiply your exponents. You should be pretty familiar with using these rules, especially on that FRQ number 4. You're probably going to have to do some reduction or reducing of an exponential function. So really knowing these rules is pretty simple. So here's an example of what I'm exactly talking about. Let's reduce this function using our exponent rules. So let's make this a single base with a single power. So first on top, we're multiplying. So we're going to add those exponents. That's 3 plus x. Now in the denominator, the first thing I want to do is I want to kind of get some bases that are the same here, right? So I could write 16 as 2 to the 4th. But it already has the 3x there. And what do you do with the double power? You multiply and then times 2. So on top, I have 4 raised to the 3 plus x. In the denominator, I have 2. And then 4 times 3x is 12x. But then I'm also going to add the 1 that's right here. So 4 times 3 to the x, or 4 times 3x, excuse me, is 12x. And then again, I'm multiplying with the same base of 2, so I can add those powers. So that's why I get the 12x plus 1. Now, I can continue to make this go even further because that 4 in top could be written as 2 squared. And that 2 squared is all raised to the 3 plus x. And then the denominator, I have 2 raised to 12x plus 1. So now, on top, I have a power raised to a power. So I'm going to multiply. So that's 2 raised to the 6 plus 2x. Again, you got to distribute, right? Because that 2 gets multiplied by 3 plus x. Your 2 powers multiply. So I get 6 plus 2x over 2 times 12x plus 1. Now, remember, I'm going to subtract. Because when you have division with the same base, you're going to subtract your exponents. So final answer here, I have a base of 2. Let's see here. 6 plus 2x. And I'm going to subtract 12x plus 1. I'm subtracting my exponents. So that's going to be 2 raised to, well, that's going to be 6 minus 1. 6 minus 1 is going to be 5. 2x minus 12x is going to be negative 10x. So there's my final answer. It's kind of ugly, but there's my final answer in terms of one base of 2 and one exponent, 5 minus 10 to the x. That's typically going to be on that fourth FRQ question for AP Precalculus, where they're going to give you something like this with multiple different bases, multiple different powers, and you got to combine it all, reduce it all to get to one base, one power. Hopefully that makes sense. All right, let's look at another problem here. I kind of actually did a problem like this earlier, where we want to put this into that more generic form, a times b to the x. Again, this is actually really, really easy to do. So the first thing I'm going to do is I'm going to separate the 2 to the x from the 2 to the negative 3. I'm using my addition rule for common bases backwards. So right, if I had it written like I have it in red here, you'd say, oh, I could add those bases. X plus negative 3 is x minus 3. But I'm just pulling them apart. That way I'm separating that 2 to the x, because again, that general form, I need a base to the x and nothing else. But what I want to do now is clean this up, because that 2 to the negative 3 can move to the denominator, just like that, where now it has a positive exponent in the denominator, and then times my ratio of 2 raised to the x. Now, 2 cubed is, of course, 8, so I get 3/8 times 2 to the x. So all I did was I rewrote this first function into that more general form of an exponential function. All right, let's now move into the next big part of Unit 2, and that is logarithmic functions. So here's a very generic, general logarithmic function. So we have a times log base b raised to the x. And logarithmic functions are inverses of exponential functions. So the key thing you need to know when it comes to logarithmic functions is this really general kind of idea, that if you have log base b of w equals x, right? This is nothing more than the base b raised to the x equals w. These two statements are technically equivalent. They're just in different forms. Exponential form versus log form. But keep in mind that logs equal the exponents. That's what logarithms are. They are exponents. So I equal my exponents. If I say, what is log base b of w? Well, that's x. That x is now my exponent. My base is the b, and I equal the w. If you can understand that general rule, that's going to really, really, really help you. So if somebody says, hey, what is log base 2 of 99? Say, well, okay, what is log base 2 of 99? Well, I don't know. I'm going to call it x. I don't know what it is. But I do know that that statement is equivalent to 2 raised to the x equals 99. So 2 raised to what number equals 99 is the answer to that logarithmic function. So again, logarithmic functions are pretty easy. They're pretty simple to work with, but a lot of kids struggle with them. But if you just understand this general idea of how they equal exponents, they should actually be pretty easy. All right, now let's quickly talk about what logarithmic functions do. So here, input values of general form logarithmic functions change proportionally as output values increase in equal length intervals. This is literally the inverse of what I said earlier with exponential functions. So here we see that the input values are getting bigger and bigger, or smaller and smaller proportionally. It's the output values that are changing that are increasing in equal length intervals. So again, an easier way of actually saying that is the growth here is categorized by the output values changing additively. So it's the output values that are going up, maybe by up to, they're changing additively as the input values are changing multiplicatively. So again, the inverse of an exponential function. Now here is a graph of a logarithmic function. Very basic logarithmic function. Now, if you remember inverses, that's a reflection across the line y equals x. So if we take any of those exponential functions we were looking at earlier and reflect them across that line y equals x, we get a logarithmic function. So this particular logarithmic function has an a value that's greater than 0. If an a value is greater than 0, we're going to see this growth. It's getting bigger, but it's growing at a slower rate, which is why we see that it's concave down. So it starts off getting big really, really quickly, and then it slows down, and it's always going to be positive. The entire graph is increasing, it's always increasing, but it's increasing at a slower and slower rate, which is why it is concave down. Now here we see that same function, but here our a value is less than 0. God, I'm so full of typos. I'm so sorry, guys. I really wanted to get this video out to you quickly, and that's why I kind of have some typos here. But anyway, this is should be negative. A value is less than 0. That's negative. Again, this is just a reflection across the x-axis. So now we see that we are decaying. We're getting smaller and smaller, but we're doing so at a slower and slower rate. But that rate is negative. So again, it's concave up. But this is where you got to really, some kids really struggle with this. It's concave up. Definition of concave up is our rate of change is increasing. But here, all of our rates of change are negative, right? The entire function is decreasing. So any rate of change across this function is going to be negative. But as we move throughout the function, those rates of change are getting less and less negative. When you get less and less negative, you're actually getting bigger. The rate of change is getting bigger. Even though it's negative, it's getting less and less negative, which means it's getting bigger, hence increasing. And that's why we see concave up. All right, so now the next most important thing when it comes to logarithmic functions is really understanding those log rules. Again, this is really more of an Algebra 2 thing, but we got to make sure we take the time to review them. When we have multiplication inside of a log, we could separate that with addition. When we have division inside of a log, we could separate that with subtraction. And here we have a power inside of our log, and that power could fall down in front of the log through multiplication there as well. That's called the, this first one's called the addition rule, then we have the subtraction rule, the difference, and then we have the power property. All right, so let's actually show how these are used. This is, again, another great fourth FRQ question where we're going to use these rules to condense or reduce or simplify a logarithmic function or expression. So imagine if this is our logarithmic function and we wanted to express this as a single log. Now, where is my base? Now, I hope you guys remember, if there's no base written, it's implied that it's log base 10. Or if we want a log with base e, we use the natural log, but any other base, we would see it, like if it was a 2 or 3 or 5 or something like that. So the first thing I'm going to do is I see that we have a log plus a log, so I'm actually going to bring those together, but I can't do that until I move this 2 up here as my product or my power property allows me to do. So I'm moving that 2 up there as a power. Then I'm going to bring the addition of 2 logs together with multiplication inside. So we have log of x plus 2 times x squared minus log of x minus 4. Now, in this first one, I mean, you don't have to, but you can feel free to distribute. That's going to be x cubed plus 2x squared minus log of x minus 4. Now I'm going to bring this together. Again, 2 logs being subtracted can come together with division. So we have log of x cubed plus 2x squared divided by x minus 4. So there is my final reduced, condensed, simplified logarithmic function where we only have one log with one base, and then inside of that log is x cubed plus 2x squared divided by x minus 4. Now listen, I could do 30 more problems like this of different variations, different types, but I don't have time for that in this video. I just want to kind of give a quick summary in this video of all these different things. But this is just a great example, and I hope everybody understands exactly what I did here to condense that down. All right, now the next big part that we work on is after we truly have a good understanding of exponential functions and logarithmic functions, we want to be able to solve exponential equations and solve logarithmic equations. So again, there are countless examples out there of different levels, easy, medium, and hard, but I kind of just want to take a look at one right now. That way we could see the idea of how to solve an exponential function with logarithms. So here we go. Here's an exponential function, which simply means my variable is in the exponent. So of course, my variable is in the exponent. It's an exponential function. All right, so the first thing I want to do is I want to isolate the base and the exponent. So I'm going to subtract 2. I get 96. That's pretty easy, right? That's not difficult math there. Then I'm going to divide by 3. Hope everybody knows what 96 divided by 3 is. And you know what? If you don't, grab a calculator. Can't be afraid. 96 divided by 3 is 32. So we get 32 equals 2 raised to the x plus 2. Now, once all that other stuff is gone, then we don't necessarily need those parentheses. Now I want to solve this. But how do I solve when the x is in the exponent? Well, logarithms, of course. So I'm going to turn this into a logarithmic statement. So my base is going to be 2. I'm going to equal the exponent, and inside the log is the other side, that's the 32. So again, it's log base 2 of 32 equals x plus 2. You always equal the exponent. So I literally just turned this into a logarithmic function. Now to solve for x, all I have to do is subtract 2 from both sides. But don't subtract 2 from the 32. Remember, log base 2 of 32 is its own number. It's its own value. So we get log base 2 of 32. And, put brackets around that because it's just a number. Take that number, subtract 2, and that's x. Now, in some problems, you could simplify further because log base 2 of 32 is something that you guys should know. Log base 2 of 32. If I said, I don't know what that is, we'll call it x. So 2 raised to the x is 32, and I hope everybody knows that that is 5. So log base 2 of 32 is 5. 5 minus 2 is 3. So our final answer for x is 3. Nice and simple. Now, actually, I want to show you another way that some teachers teach to do this without logarithms. When we were at this stage right here, what we could also do is this. We could say, well, wait a minute. If I have the same base on each side of an equation, then the exponents must also be equal. So we can rewrite 32 as 2 to the 5th, which equals 2 to the x plus 2. Again, you can't always do this though. Some numbers can't be written with a base of 2. But in this case, 32 can be written with the base of 2. So I wrote that as 2 to the 5th. Then, when you have the same base, your exponents must also be the same. Therefore, 5 equals x plus 2. Subtract 2 from both sides, and we get 3 equals x. That works. That's awesome. That's a cool way of doing it, but you can only do that if you could write that other side with the same base. Otherwise, you got to go and turn it into a logarithmic statement like I just did. All right, now let's go ahead and take a look at solving a logarithmic function. All right, so if I'm going to solve this, the first thing I want to do is I want to combine my logs together. The less logs, the easier it is to solve. So I have log of addition right here. And remember our log rules, I'm going to bring those logs together with multiplication. So we have log base 2 of 3 minus x times 5 plus 2x. And again, maybe you want to throw that in brackets. That way you know that's all inside that log, which equals log base 2 of 14. Now, I'm actually going to show you guys 2 different ways to do this problem right now. First, once you have a single log on the left and a single log on the right of the same base, then we know that the insides also must be the same. So if once we have a log base 2 on both sides, then we know that this value inside that log and this value inside that log must be equal. So we can essentially get rid of the logs. So we have 3 minus x times 5 plus 2x equals 14. And this is going to be a basic quadratic we could solve with factoring. But let's go ahead and do it anyway. It's a good review, especially for the AP exam. 3 times 5 is 15. 3 times 2x is 6x. Negative x times 5 is negative 5x. And negative x times 2x is negative 2x squared equals 14. To solve a quadratic, I want to get everything on one side, preferably with the square term being positive. So I'm going to move everything to the right-hand side. So I'm going to add 2x squared. My 6x and my negative 5x make a 1x. I'm therefore going to subtract over. So I'm going to subtract over that 1x. And I'm also going to subtract over that 15. And 14 minus 15 is negative 1. All I did was bring everything to the right-hand side. Now I could use the quadratic formula, or I could factor, and this is a fairly easy one to factor. So to break apart a 2x squared, we need a 2x and an x. To break apart a 1, we need a 1 and a 1. Now, to get that negative 1 in the middle, I do want a negative 2x to be generated and a positive 1x to be generated. That's going to make that negative x in the middle. Then I'm going to use the zero product property. 2x plus 1 could equal 0, which means x equals negative 1/2. Or x minus 1 could equal 0, which means x equals 1. Now, it's important when you're working with logarithmic functions to check for extraneous solutions. Now, the inside of a logarithm can never be negative. So if something makes the inside negative, then it's an extraneous solution. Now, obviously, 14 is already positive, so nothing I could do there. Let's check 1. 5 plus 2 times 1 is going to be 7. That's a positive number. 3 minus 1 is 2. That's a positive number, so it checks out. Now we're going to check out negative 1/2. 3 minus negative 1/2 is going to be a positive number. That's good to go. 5 plus 2 times negative 1/2. That's also going to be a positive number. 2 times negative 1/2 is negative 1. But then again, 5 plus negative 1 is still a positive number 4, so we're good to go. So that works out there. Now, I told you I was going to show you one more way that we could solve this problem. All right, the other way we could solve this problem is to continue, before we do anything with logs, continue to get everything on one side. So now I'm going to take this log base 2 of 3 minus x times 5 plus 2x. And I'm going to subtract, there should be a bracket there, sorry. I'm going to subtract over the log base 2 of 14 and make that equal to 0. Now we could say, subtraction of 2 logs, I could condense using division. So that's going to be log base 2 of 3 minus x times 5 plus 2x, all divided by 14 equals 0. Now, once you have a single logarithm on one side, what we could then do is convert it to an exponential function. We could turn, to get rid of the log, we need its inverse, which is an exponential function. So to do that, I'm just going to follow the definition. Base of 2 raised to my exponent, logs always equal the exponent, so my exponent is 0, equals the 3 minus x times 5 plus 2x, all divided by 14. Now, 2 raised to the 0. Well, anything raised to 0 is a 1, so that turns into a 1. Multiply the 14 over. The opposite of divide by 14 is multiply by 14, and I get 14 equals 3 minus x times 5 plus 2x. Now remember, that was the exact same point we got to earlier when we said, hey, when you got a log on each side of the same base, then you can essentially get rid of those logs, and we know that 3 minus x times 5 plus 2x equals 14. Multiply, factor, get everything on 0, then factor. And again, it's the same exact answer. So 2 different ways to approach that problem that both result in the same answer. All right, now midway through Unit 2, they kind of stop talking about exponential and logarithmic functions for a moment, and they talk about compositions. So composition functions use this symbol right here, this open kind of circle. And this means we're going to compose one function of another function, which basically means we're going to put a function into another function. So f composed of g literally means that we're going to take g of x and plug it into f of x. Or if we switch it around, again, whatever comes second is what goes into the first, right? So it's g composed of f. G composed of f. So we're going to take f and plug it into G. It's that simple. Compositions are definitely going to show up in multiple choice, and they're 100% going to show up on that first FRQ. In fact, it's almost a guarantee that in that first FRQ part A, they're going to ask you about a composition function. So here's an example. We have 2 functions, and I'm going to say, hey, I'm going to define h of x, a brand new function that is designed to be f composed of g, which means we're going to take g and plug it into f. So if we say, hey, let's find a function h of x, well, we literally need to do the composition. We're going to take g, plug it into f. So I'm going to take g, x plus 2, and I'm going to plug it into f. So we get 3 times x plus 2 squared minus 5. So again, notice how I literally took g and I plugged it into f. There you go. There is the composition function. Now I could reduce that obviously if I do 3 plus 2 and square it out, x plus 2 times x plus 2, multiply it out, distribute it 3, combine the like terms with that -5, and you can reduce it. But one thing they're definitely going to do on the exam is they're going to do something like this. Hey, what is f of 4? So, or excuse me, what is h of 4? So now we got to remember, okay, so the first thing we got to do is, if we define this as f with g of 4 plugged into it, because x is 4. So the first thing we want to do is take 4, plug it into g, because that's what happens first inside the parentheses. That's pretty easy to do in your head. 4 plus 2 is 6. So now we get f of 6, because g of 4 is 6. Now what we have to do is take that 6 and plug it into f. So that's going to be 3 times 6 squared minus 5. Well, 6 squared is 36. You guys all know that. Times 3 is 108. Minus 5 is 103. Don't be afraid to use your calculator as well if you need to, but our final answer would be 103. Now, I could get that exact same answer if I were to plug 4 into my new function that I created by actually taking g and plugging it into f. So either way, you could do it step by step, or you could build your new function first, f composed of g, and then plug it in, or you could plug it in into g first, get an output, take that output, plug it into f, and you'll get your value as well. So hopefully compositions of functions are not too bad. Even if you have a table or a graph, you could still compose functions of each other. You won't be able to get a nice, algebraic answer like I did right here. But you definitely could say, okay, hey, if they want me to, f is maybe an input-output table, and they want me to find what f of 2 is. So look at the table, use an input of 2, get an output. Then now I got to take that output and plug it into a different function, w. So I'm going to take that output, plug it into w to get my final answer. So again, you could definitely compose functions of functions, whether you got analytical form like I do of here, or graph or tabular form as well. All right, up next is inverse of a function. Now, to find the inverse of a table of outputs and inputs, literally just switch the outputs and inputs. Like, that's it. So take all of your inputs, move them to the outputs, take all of your outputs, move them to the inputs, and now you have the inverse of that function. But be super careful. But make sure after the switch, each input has only one output, or else it's not invertible. Because if you're going to call something an inverse function, well, it needs to be a function, and the definition of a function is every input has exactly one output. So once you make that switch, just look, does every input go to one output? Or did I just create an invertible function because I have the same input of like 2, and on one area it goes to 5, but another place it goes to 7. Well, you can't have 2 to go in 2 different places, so that's why you'd be an invertible. So be very careful when you do that. Now, if you're trying to find the inverse of a function analytically, it's very simple. Switch the x and y's, then solve for y, and label that new answer as your inverse function. But again, make sure that each input has only one output, or else you might have to make some adjustments to make it be invertible. So let's look at an example. So here's a function. It might say, hey, find the inverse. So first off, everybody knows f of x is the same thing as y. That's pretty easy. Then I'm going to switch my x's and y's. And now I'm going to solve for that new y. So I'm going to add 5. Divide by 3. And how do you get rid of a square? Well, you take a square root. But remember, when you take a square root, you need a positive or a negative. Okay, now that I have solved for y, I'm going to label that new function as my inverse function. So the inverse function is plus or minus the square root of x plus 5 divided by 3. But wait a minute. Is this truly a function? Well, if I plug in a value for x, I add 5, I divide by 3, but I have that plus and minus, which means I actually have 2 answers. So I plugged in a value for x, but out came a positive square root and out came a negative square root. Well, you can't have 2 outputs. So this would not be an invertible function unless we restricted the domain. So maybe we said, hey, this domain can only exist to certain values. Therefore, when I invert it, I only get half. Like maybe I'm going to restrict it to only the positives. So I'm not going to even worry about this negative right here. Now, all of a sudden, I do only have one output. But that function would have to be restricted. So again, just really briefly kind of show you, this is going to be a terrible graph, but 3x squared minus 5 is a parabola, right? Something like that. And the idea is that if I reflect this parabola across the line y equals x, I'm going to get something like this, which is not a function because we have multiple inputs that have more than one output. But if we say, hey, we're only going to use this side of the parabola from the vertex on, I'm only going to use that side of the parabola. Then when I invert that, I'm only using this portion of my answer, which would only be that positive square root. And if that's the case, now I am invertible because my function only has, one side of it, or only one output for every input. So hopefully that makes sense, but I just want to make sure I'm very, very clear on that because it could definitely come up on the exam. Now, of all the types of functions out there, the one that is the hardest to find the inverse of are rational functions. So let's really quickly do this because this could definitely come up on the multiple choice exam or maybe even the free response. So once again, I'm going to change that f of x to a y. Everybody knows how to do that. Then I'm going to switch all of my x's and y's so that y becomes an x. And then both x's become a y. And that's actually what makes this kind of hard. But I'm going to walk you through it right now. All right, so the first thing I'm going to do to now solve for my y, but what's tricky is that I got two y's, but we can do it. It's not that hard. I'm going to multiply both sides by 3y minus 4. So I have x times 3y minus 4 equals y plus 2. Then I'm going to distribute that x, so I get 3xy minus 4x equals y plus 2. Now what I want to do is I want to gather all of the terms with a y on the left and everything without a y on the right. So I'm going to add the 4x to the right-hand side and subtract a y to the left-hand side. So any term with a y is going to go to the left-hand side, and any term without a y is going to go to the right-hand side. So I added the 4x to the right, subtracted the y from the left. Now what I'm going to do is on the left-hand side, I'm going to factor out that y that's common. And again, when I factor out that y, I'm dividing it away. So 3xy divided by y is just 3x. Negative y divided by y is the negative 1. And then the final step to solve for y is to divide both sides by the 3x minus 1. So I get 2 plus 4x divided by the 3x minus 1. So my inverse function of that original rational function is 2 plus 4x over 3x minus 1. For some reason, that type of problem is extremely challenging for students, so hopefully I walked through it pretty slowly, but also quickly enough that I wasn't wasting your time. But I really wanted to make sure I showed you how to find the inverse of a rational function. All right, now we're going to move on to the last big part coming out of Unit 2, which is regression models. Now, the whole idea of a regression model is you have a scatter plot of some real-world data. And what you want to do is you want to put a model, a function, through that scatter plot that can be used to make predictions. Now, you could have linear regression models, quadratic regression models, exponential regression models, or even logarithmic regression models, all based on the shape of your scatter plot. So here's a quick example of a scatter plot. And I say, I want to put a model through this. What type of model can I use? Well, an exponential model that has some exponential growth would probably be a great value to use, or a great function to use, because it definitely looks like I'm increasing at an increasing rate, which would, make sense for an exponential model. Now, that exponential model is going to look something like this: y equals a times b to the x. But what I really want to make sure everybody understands is that that model is just making predictions. The actual purple dots are real, actual values. In the line makes predictions. In every prediction is off a little bit. Now, the distance, vertical distance, that each point is from the model is called a residual. So how do you find the residual value? You take your actual y minus the predicted y. So once again, if I kind of draw, and this is just a rough drawing, but if I kind of draw that exponential model on top of that function, or on top of that scatter plot, what we'll see is that some points, I'm actually going to point a couple out here. For example, this point right here is above the line. This vertical distance is the residual. So the point on the model, on the red model, that's my predicted value. That's what I predicted the y value to be. but the actual point at that x value was above it. So positive residuals are where your model was an underestimate because my model was underneath the point. And what you're going to see is you're going to see lots of positive residuals. Now, this one's kind of a bigger one. This one's kind of a bigger one because remember, it's that vertical distance. These are kind of a little bit medium size. And over here, we actually have some smaller ones. This one right here looks to be almost perfect, but still might be off by a smidgen. Then we have negative residuals. So a negative residual is when the point is below the line. Again, it's that vertical distance. It's the residual value. Now, that's because if I take the actual y and I minus the predicted y, since the predicted y is above it, I'm going to get a negative residual. A negative residual simply means that the prediction from the red model was over estimate. It was over top of what actually occurred. Now, what's kind of cool here is that when you make the best model, your model should go through the data. And if your model is really doing a great job going through the data, it's going to naturally produce positive and negative residuals. And some of those residuals are going to be bigger, and some of those residuals are going to be smaller, and some of them are going to be more medium. That's just what happens. Now, let me kind of show you what I'm talking about here. Imagine if I was really dumb and I said, hey, I'm going to use a linear line, a linear function to model this data. And I would do something like this. Now, I hope everybody recognizes that that's a terrible model. An exponential model is way better. But notice what happens when I do this. There's actually a pattern in my residuals. All of the residuals in the beginning are positive. And they actually started out kind of big and then slowly got smaller. Then in the middle, I had all negative residuals, starting out kind of medium or small, then getting a little bit bigger. And then at the end, I have all positive residuals. So if I think about my residuals, there's a pattern to them. All positive, then all negative, then all positive. That's bad. That's a sign that my model, my linear model, was not very good, not appropriate for this data. When again, I want to go through the data, and a model that goes through the data is going to produce a nice mix of residuals. Positive, negative, big, small, medium, everything. So this is really important to note that a residual plot that shows no pattern is a sign that the regression model used is appropriate for your data. That's a big time multiple choice question. They might show you a couple different residual plots and say, which one indicates that our model is most appropriate? The one that looks the most scattered. Again, we want positive, negative, big, small. And again, residual plots would be like if we just graphed our residuals. So we're going to see a zero line in the middle, and we're going to see some positive residuals, and we're going to see some negative residuals, and some are small, and some are negative but small, some are medium and positive, some are medium and negative, and some are big. That's a good residual plot. Again, it's mixed up. It doesn't show anything. That means your line, your model, is going through your data. All right, now the final thing I want to talk to you about is how we can actually create a model, because this is going to happen on that second FRQ. So here's an example. There's lots of different examples. I can't go through them all in this video, but here's a good example that I can actually talk about a lot of things with. So we have 2 points, and we want to find an exponential model that we could use with these 2 points. So an exponential model, remember, looks like this: a times b to the x. So basically, we have to solve for a and b. So the first thing we want to do is create 2 equations based on these 2 points. So the output is 10 when the input is 3. So if I'm using an exponential model, my x is my input, my y is my output. So if I plug in 3, I get 10. But I also know that 42 is my output when I plug in 7. So there are my 2 equations I'm going to use to generate my a and b value. That way I could build my function or my model, right? Okay, now how do I solve this? Well, it's actually really, really easy. Follow along with me here. I'm going to first take this first one. I'm going to solve for a. How do I solve for a? I'm going to divide by b cubed. There's a. Now I'm going to take that a value and I'm going to substitute it in right there. So I have 42 equals 10 over b cubed times b to the 7th. Then I'm going to use my exponent rules. B to the 7th divided by b cubed, I could subtract. 7 minus 3 is 4, so I have 10b to the 4th. Then I'm going to divide by 10, and I get 4.2 equals b to the 4th. Now, how do you get rid of a 4th power? You could do 2 things. You could use a 4th root, or raise both sides to the 1/4. A 1/4 power is the same thing as a 4th root. So if I take 4.2 and I raise it to the 1/4 power, I get 1.432. Now that's rounding it to 3 decimals, which is a smart thing to do here for my b value. So now that I know my b value, I'm going to actually come back up here and I'm going to plug it in to find a. So I get 10 divided by 1.432 cubed equals a. Grab a calculator and do that math. Definitely going to need a calculator on this section. On that second FRQ, you will be allowed to use a calculator. So I get an a value of 3.405. So my exponential model is going to be 3.405 times 1.432 raised to the x. So that's going to be an exponential model looking something along those lines right there where we see our values are on here. Now, one of the points that we know is on this model is 3, 10, and another point that we know on this model is 7, 42. Now, another very popular FRQ question that will come after this is what is the average rate of change between those 2 points? Well, the average rate of change is found by simply connecting those 2 points with what we call a secant line. A secant line connects 2 points together. And we say, okay, that line, the slope of that line or the rate of change of that line is my average rate of change. All right, so how do I find that average rate of change between these points 3, 10 and 7, 42? Well, it's so simple. To find that average rate of change, we're simply going to subtract our y's on top, 42 minus 10, subtract our x's on the bottom, 7 minus 3. So we get 32 over 4, and 32 over 4 is 8. So our average rate of change is 8. Now, let me draw that picture one more time, because I think that picture is going to really help. So here's that exponential model. Here are those 2 points, 3, 10, and 7, 42. And here is that secant line that we just connected them with and found the average rate of change. Now, the other thing we could do is we could use that line to help us make predictions. Now, that secant line. Now, how do I find the equation of that secant line? Well, okay, come on, go back to algebra. How do you find the equation of a line? Well, you need a slope. I already have the slope. It's 8. That's the average rate of change. And I need 1 point. Well, I got 2 points. So it doesn't matter which one we use. I'm going to use point slope form. Point slope form looks like this. I really hope everybody remembers this from algebra class. But it doesn't matter which point you use, but you will need the slope of 8. So I'm going to use that first point, 3, 10. So y minus 10 equals 8 times x minus 3. And then I'm simply going to add that 10 over. So I get 8 times x minus 3. And I'm going to add that 10. Now you could distribute that 8 if you want. Knock your socks off, and then you could combine like terms. But this works. But again, I want everybody to be very clear what I'm doing here is I've found the equation of that secant line connecting those 2 points, which I was looking at the average rate of change for. Now, what I could do is I could use this line right here to make predictions. So let's talk about, let's do 5, for example. Let's predict what happens when x equals 5. Now remember, this point right here was at 3. This point right here was at 7. So 5 is somewhere in between. So let's go ahead and plug in 5. So we get 8 times 5 minus 3. 5 minus 3 is 2 plus 10. 8 times 2 is 16. 16 plus 10 is 26. Hope everybody follows my math there. Now, is that an over or under estimate? Well, look at the graph. I plugged in a value in between 3 and 7. In between 3 and 7, my line, my blue line here is over top of the model. So 5 is, I don't know, somewhere right around here. So there's my point right there. So I got 26. That 26 came from using that blue secant line. But if you look at my graph, in between 3 and 7, the model in red is below my prediction. So my prediction was, in this case, an overestimate. It was over top. Now, if I were to pick a value like, let's see here, like 10, right? X value of 10. Now, 10 is over here somewhere, right? 7, 10 would be over here somewhere. So this time, my line is going to be over here. My prediction is going to be right there. Let's actually do it real quick. Y equals, again, I'm using my secant line to make these predictions. 10 minus 3 is 7. 8 times 7 is 56, plus 10 is 66. Now, on this side of the graph, to the right of 7, now all of a sudden, my exponential function in red is going up at an increasing rate, which means it's going up faster and faster and faster, but my linear secant line is going up at a constant rate. So to the right of 7, now notice that my prediction from that secant line is below the red model. So in between 3 and 7, my secant line is above the model. Outside of 3 and 7, my secant line is below the model. So those are just some important observations. These types of questioning that I'm talking about right now is all going to be on that second FRQ, where you're first creating a model using some given points, like I did on that previous page where I found my A and B. But then we could take those 2 points and find an average rate of change and find the linear equation connecting those 2 points. Then we could talk about how predictions from that secant line are going to be a little bit different than the model has. But it's important that you make that graph, because that graph allows you to see exactly what I'm saying, that, in between 3 and 7, our secant line is above the graph. Outside of 3 and 7, our secant line is below the graph. And I hope everybody knows what I mean by that, right? So look over here, my line outside of 3 and 7 are below the red model. And then in between, I'm above the red model. So those are all kind of important things that I hope that you're talking about and going over in class. That way you can continue to learn and understand them, and how all of this stuff is intertwined. We can have functions, but then we can find average rate of change between 2 points. We can create those secant lines and see how we could use that secant line to make predictions, but those predictions are going to be off from the model. I mean, there's tons of fun information here, and I know I'm going through it very quickly, but that's the whole point of this video, is just to be kind of a summary video of it all. But that's it. Those are the big, huge, enormous concepts out of Unit 2, and there's tons of more small details, but I really want to make sure in this video just kind of hit the big things that I know typically come up on the exam. So hopefully you're ready. Hopefully this video helped you a little bit. That way you can prepare for the exam. Good luck.